Thank you. So before I start, the title of my talk is Detecting the Rare and Complex, ML for Precision and Efficiency at the LHC. So I've tried to keep the topics and what I cover. You hear me still?
My bad.
Okay, good. So I've tried to keep the topic of what I discuss relevant to multi-boson searches, but it is also very generic with very generic examples. So I think vector boson scattering, vector boson fusion, it's great examples of where machine learning will help us get better in the coming years. And the reason for that is that it kind of touches upon all of the points we will have to deal with at the LHC in the future. So as most of you probably know, the LHC at the end of the LHC will only have collected 10% of our final data set that will be collected at LHC and High Lumi LHC. So during High Lumi, we will collect the restoring 90% of the data. So that means we have to deal with massive, massive amounts of data, extremely high peak luminosities. So we need to be able to generate simulation enough to be able to do good comparison data to Monte Carlo, and we need to be able to process all of that data. And VBS is really one of those precision measurements where you will finally be able to measure extremely cool things with the statistics we'll have available. Also, vector boson scattering, vector boson fusion is one of these processes that will benefit from us having better detectors. So as we move towards the future, towards this very busy detector, the collision data that we will have during the high luminosity LHC, the experiments are investing in better detectors in order to have better data. And especially with for instance, VBS, you have these two very forward quark jets that will benefit from, for instance, better detectors in the forward region. It's another example of the future for VBS. Also, in analysis, you're trying to measure an extremely rare process to high precision, and we will want to be able to squeeze the most out of the data we have at hand. Yes, it will be 3,000 inverse femtobarns. There will also be a lot of background, so we need to be able to increase S over root B as much as we can. And in this talk, I hope to convince you that machine learning will be a tool for us to, one, manage the huge data rates and the compute we will need for simulation, two, to reconstruct complex patterns and very complex particle detectors, and three, to enhance S over root B for very rare measurements. So one of the things I think is very exciting with these type of multi-boson searches is that you have this event with a very interesting topology with a lot of event information. So for instance, you have these forward quark jets where it would help you a lot if you can do quark gluon separation, for instance, to reduce the background. It would help you a lot if you have better jet resolution, which you can get with machine learning. It would help you a lot with pileup mitigation, which you can do with machine learning. Also, vector bosons, 67% of the times decay all hadronically. With machine learning, you can really do very good jet tagging using the jet substructure and maybe even having access to longitudinal versus transversely polarized vector bosons in the alhadronic final state. So I think what you are doing is an example that we use a lot when we want to show the gain you can get with using machine learning in particle physics analysis. Okay, so before we dig into that, I also wanted to go through a little bit the backstory behind machine learning and high energy physics and how they've interacted and how they've developed amongst the years. The reason being that CERN celebrated its 70-year anniversary this September. So here you can see 17th of May, 1959, where they dug the first shovel at Mera to build the CERN site. So I wanted to look a little bit at how these two fields, high energy physics and machine learning, have developed in parallel. So September 29th, 1954, 12 nations went together and signed the convention that became CERN. And in 1954, it was interesting because it was just 5 years after Turing proposed his famous Turing test. And if CERN was born September 29th, 1954, AI was also born around the same time. So in 1955, McCarthy, Minsky, Rochester, and Shannon proposed the first Dartmouth Summer Research Project on artificial intelligence. Since this is the very first time the term artificial intelligence was coined, and what they wanted to do was to have a 2-3 week summer school dedicated to discussing artificial intelligence. So AI was basically born with this summer school, and it was put together by some really impressive people. You have McCarthy here, who actually invented Lisp, the programming language. Minsky, one of the fathers of AI, founders of the MIT AI labs. Rochester, that invented the first commercially available IBM computer. And Shannon, which is the father of information theory. So some very important people. So CERN AI, both born around this time. We stepped forward in 1957. We had our first accelerator at CERN, which was the very first instrument to provide us with powerful particle beams. And if the synchrocyclotron was born in 1957, the perceptron was born in 1958, which is one of the fundamental building blocks of modern neural networks. It was a paper by Frank Rosenblatt that worked together with Minsky, actually, that proposed the Dartmouth Summer School, and proposing this one-layer neural network that he predicted would eventually be able to learn, to make decisions, and to translate languages. So first beam and first neural network. Speed forward, we had now at this point, 2012, very good, well, before 2012, with kind of this prediction of electroweak symmetry breaking, supersymmetry. We had very good motivation for discovering new particles at the TeV scale. So the LHC was proposed, the LHC was built, the LHC started taking data in 2008. Basically with the hopes of discovering supersymmetry and a Higgs boson with a mass below 1 TeV. Then, due to magnet failure, as we all know, we had to switch off also in 2008, but in 2010 until 2012, we were able to collect enough data to discover the Higgs boson, and here is the Higgs 2 in the diphoton final state with a 5.7 sigma discovery. So we discovered something fundamental in high energy physics. And what happened in AI at the same time was that they discovered something fundamental in AI for the same reasons and with the same tools that we discovered the Higgs. And that was that if you had enough compute and enough data, a machine would be able to perform well on tasks that a human would be able to do very well. So September 30th, 2012 was when the AI revolution started with a network called AlexNet, named after Alex Krzyzewski, which designed this model. It was based on machine learning methods that were known for 20 years. And it demonstrated that it could beat state-of-the-art computer vision methods by a huge margin. And that was when people were really baffled by what these models could do. AlexNet was also done together with Ilya Sutskever, which is very much in the news these days, is one of the founders of OpenAI, and Geoffrey Hinton, which we also all now know since he got the Nobel Prize in Physics. So 2012, with compute, big data, we discovered the Higgs. 2012, with compute and big data, we discovered the power of AI. So where are we now? Well, now we are at this point where the Nobel Prize in Physics went to AI. So Hopfield and Hinton got the award for inventions which used physics to build fundamental techniques in machine learning. So the Hopfield network, which uses basically spin to minimize the energy of the system. He does the same for neural networks. And Hinton that use statistical physics basically in what's called the Boltzmann machine. Hinton should have gotten the Nobel Prize in something for backpropagation, for instance, but got it for these building blocks. And at the same time, so this is now on the physics side. At the same time in AI, we are changing the building blocks fundamentally. So Max Tegmark this year proposed a replacement of what is called the perceptron that we talked about before. So what kind of makes neural networks so powerful is that we have this guarantee called the universal approximation theorem that says with at least a single hidden layer that's arbitrarily but limited in its width, you can approximate any function. And Max Tegmark, a physicist, proposed a new type of building block. So no longer learning the weights of a neural networks, but learning the activation functions using the Kolmogorov-Arnold representation theorem that has the same type of guarantee, but with different operators. So now these things are merging. We have physicists changing the building blocks of neural networks, and we have computer scientists getting the Nobel Prize in physics for using physics to do AI. So these two fields are getting very, very close. Okay, so what all of this has brought us is, especially in science, what we call accelerated discovery. So I think one of the coolest example is AlphaFold. So AlphaFold is a huge transformer network that was used in order to predict, given a set of amino acids, how the protein would fold. And how the protein folds is basically essential to its function in the human body. And here on the left, you can see two proteins. You can see one which is, you can see the green as the experimental result after measuring the actual folded protein, and blue is the prediction. And blue is now the prediction from a neural network. And this used to be a very difficult task. So before AlphaFold, which is from DeepMind, we knew roughly 11% of how the 20,000 proteins in the human body fold, and those proteins are essential to how we function. And after AlphaFold, we know over 98% of how these proteins fold. So that's a huge kind of accelerated discovery achievement. So after AlphaFold was published, they did this very nicely. First, they won this protein folding software contest, which was huge, where they could accurately predict the folding of given proteins. And afterwards, they would unblind the protein and compare with the predictions of many different algorithms. They also released AlphaFold 2, made it open to scientists and with all the source code included. And after that, there's been an explosion of papers and chemistry, biology using AlphaFold. So this is huge. So that's in biology, chemistry. What I think is interesting is that we have been using machine learning for accelerated discovery in high energy physics for a very long time. So we discovered the Higgs, we discussed the Higgs discovery in 2012. What we don't talk about is that we used the data from 2010 to 2012 to claim a discovery of the Higgs, which is 5 sigma. We had evidence of the Higgs already before, that's roughly 3 sigma. So knowing that, we could already predict how much data we would need in order to claim an actual discovery. And what we knew was that if we used our normal kind of rule-based algorithms to do this analysis, we would only have enough data to discover the Higgs in 2016. If we used machine learning to enhance the sensitivity to that signal, increase the S over root B, we would be able to detect that Higgs boson way earlier. And this is a plot I really, really like. Here you can see the dataset increase factor we would need going from 3 sigma to a 5 sigma discovery as a function of the Higgs mass, which we didn't know at the time. If we used our usual approaches to select the photon for this is the diphoton search, we would need a factor of 5 more data to go from first evidence to discovery. And in 2012, we didn't have that. What we did have was a factor of 3.5 more data. So using machine learning, these BDTs, boosted decision trees, we were able to claim discovery of the Higgs way earlier than what would have been possible without machine learning. And this is not something that was just in the CMS search in the diphoton channel. It's generic. If you look at all of these Higgs channels, CMS, Higgs to gamma gamma, Higgs to tau tau atlas, VHBB, this is the years of data this is the years of data collection. The sensitivity we would have to detect this process without machine learning is significantly less than what we have with machine learning. So for instance, in this case, you go from 1.9 to 2.5 sigma, just adding machine learning on top. And if you didn't have machine learning, you would need way more data. So this really shows how machine learning can be used to do the most with the data we have at hand. And this is something that will be crucial in the future as well, because for instance, for VBS, yes, you have more statistics, but you also need to do the most you can with that statistics to enhance S over root B. Okay, so where are we today? Today we have 40,000 papers so far using machine learning, AI, neural networks, deep learning, those type of terms in their papers, which is a vast amount, and it grows more and more, especially now after the Nobel Prize. What I also think is interesting is that this is something that goes back a long way, back to 1985. So I did some archaeology to figure out who was actually doing machine learning in 1985. And I stumbled over this very strange philosophical paper, An Evolutionary Procedure for Machine Learning, which is the first time artificial intelligence and machine learning was mentioned in a physics paper from Leonard Mlodinov, which is a very interesting character. He wrote The Grand Design together with Stephen Hawking, and afterwards went on to write episodes for Star Trek and for MacGyver. And in this paper, they talk about how machine learning can be used to control a hypothetical robot called Turtle and used to navigate where this robot would go. So very, very abstract and strange paper, not really related to physics. What is the real first paper using machine learning in high energy physics is this paper by Bruce Denby, received 1987, which is the very first time you talk about neural networks and cellular automata in experimental high energy physics. And there he already talks about very relevant use cases today, which is track and cluster finding, for instance, that can solve problems in a fraction of the time required by traditional methods because they're massively parallel, and could, for instance, be used to make trigger decisions. And all of these things are things we are very focused on now: track, cluster finding, reconstruction, doing it more efficiently and using it for triggering where you have to be extremely fast. So we gave a super nice presentation in our hardware trigger workshop in 2023, where he mentions how he introduces neural networks to our community for the first time, proposing things like track finding, triggers, template matching, etc. So this is the first time we took advantage of and discussed using these techniques. So where are we now? What are we using these tools for now after all the building blocks were made and after Bruce proposed what we should be using them for? So in this talk, I want to go basically through the whole analysis flow, again, often using vector boson fusion or vector boson scattering or vector bosons in general as examples. So when we do an analysis at the LHC, what we actually want to do is measure the standard model, measure deviations from the standard model, do precision measurements of all of these measurable observables. And the way we go about doing that is by first colliding trillions of protons in the center of our detector to produce data that we can then analyze. Now, the problem for us is that we cannot just produce data and then look at it by eye and infer what that data contained. The only thing we can do is compare it to simulation, to compare it to some hypothesis. And these hypotheses we generate through Monte Carlo simulations. What we do is that we generate particle collisions that should mimic basically what happens in our detector, and we simulate how the detector responds to that. So to probe the standard model, we have the two ingredients. We have actual data that's from particle collisions inside the detector, and we have simulations, which is basically how, if this process happens, how would it look like in the detector. These two things happen in parallel. When we have those two ingredients, what we do is pass them through exactly the same software that goes from the collision that happened and produced things in our detector, the collision we simulated to happen and leaves deposits in our detector. And then we pass that information through exactly the same code that does a reconstruction of that collision using what's called reconstruction software. Then once we have a reconstructed version of the simulation, a reconstructed version of the particle collision, again, using exactly the same software, only then can we do hypothesis testing, basically. So comparing the simulation, which is usually what's this red line here, with the black markers, which is the data. So black dots from the detector, red lines from simulation. Now, why are we doing all this? Well, the reason we're doing all of this is in my two favorite plots from the LHC that was ever produced. One is precision measurements of fundamental parameters, like for instance here, the Higgs coupling as a function of particle mass, measured to extreme precision, agrees with theoretical predictions, and also to discover new particles. So for instance, here you have the 75 new hadrons we discovered at the LHC. And all of this we do to make fundamental discoveries in particle physics, like the Nobel Prize that went to Englert and Higgs for the Higgs discovery. Okay, so in all of this chain, where do we use machine learning and how? We use machine learning at all of the stages in this processing. So from the theoretical part itself, which I won't talk about at all, but it's often used to make, for instance, integrals faster, to detector design, reconstruction, data acquisition and triggering, for the simulation, generative models for simulation, detector reconstruction and tagging, and finally for data analysis. And we will go through all of these steps. One of the things that's important before we start talking about using machine learning in the way we do for computer vision is that AlexNet, for instance, where you use machine learning for image recognition, is very different from high energy particle physics. So if in normal machine learning, you try to tell the difference between a cat and a dog, for us, a quantum cat and a quantum dog is very, very different. The reason for that is quantum mechanics. Basically, if we have a collision happening, we can't look at it and say, in this collision, a Higgs was produced. No, a Higgs was produced, a Higgs was not produced, or a superposition of both of them. So we don't have labeled data at all. So that means that for every discrete event, we can't put a label on it and train a machine learning algorithm. We can't say this is a picture of the Higgs, learn what's the difference between the Higgs and some other standard model process. The only thing we can do is do collisions trillions of times, generate simulations, and basically try to constrain the PDFs with their amplitude. So you have some signal PDF here in red, some background PDF here in green, and they have some amplitude. And we can only try to constrain basically these parameters. So we have no labels for individual events. That's why we have this very complex simulation chain that takes us from roughly the size of the Higgs boson, 10 to minus 18 meters, where you have a handful of particles, passes it through hadronization, where you have suddenly 10,000s of particles, passes it all the way through a 100-meter long detector until you have millions of hits in detector channels in the final state. So in order to train machine learning algorithms where you have a label, we need to go through this extreme process. So we have roughly 40 quadrillion collisions recorded at the LHC, which is 278 petabytes of data. It's a vast amount of data. It's Netflix for 15,000 years. And then we have orders of trillions of simulated events. So in the case of discovery of the Higgs boson, for instance, we had to collide billions of protons and only a handful of them, 10, were needed to claim the discovery. So that also brings us to how we train these machine learning algorithms. We have a lot of high quality simulated data that we want to use to train algorithms, and we have a lot of unlabeled data we'd like to use. So we also will talk about supervised versus unsupervised learning. Okay, so the first step we'll go through is how we can use machine learning to enhance our sensitivity. So how to enhance S over root B. And the first thing I want to talk about is detector reconstruction and tagging, because it was one of these main tasks that we wanted to achieve when we first started using machine learning for our problems. So when I showed this plot before, I kind of put these kind of labels here already. I said, this is a VBS event. You have two very forward jets parallel to the beam pipe, and you have two vector bosons that come out of the interaction point. Obviously, in the real detector, we don't have this. We have tracks and we have hits and trackers and calorimeters, and we need to figure out basically what is what. And one of the biggest problems for us is that this is an image of a collision, which has equally spaced pixels. So it's very easy if you have an image and you want to classify it. It becomes very difficult when you have heterogeneous detectors, which are very, very sparse. And one of the main things that we started using machine learning for was for the identification of what type of particles were in the collisions themselves. So jet tagging, for instance, is really one of our benchmarking tasks. So was this jet produced by a quark, by a gluon? Was this jet produced by a W boson, by a B quark? And really trying to figure out what happened in the event. This is the first thing we kind of had to do on our own. There were no tools from the private sector that told us what to do. And it was very difficult going from such a very strange representation of an input, sparse, heterogeneous, to something that would fit through basically an algorithm that takes a fixed input array, passes it through, and gets it out on the other side. So for us, the first step was figuring out the data representation. The first thing we tried was treating the collision as an image. So we unroll the detector, and every single cell and its energy is basically a hotspot on this image. The problem for us was that when we used state-of-the-art machine learning techniques to do this, it wasn't doing well, because we had this high sparsity and we had a lot of symmetries in the problem that weren't really taken into account. Then so in homogeneous geometry and high sparsity. Then there were these kind of new inventions in language, so language modeling using machine learning. So we tried treating our jets like a sequence. The problem there was that where a sentence has a structure, so for a sentence, there's an order of the words. So in a sentence, how are you has an order. These are not permutation invariant. And for jets, we can order around the particles as we want, and it's the same jet. That's what we call permutation invariance. Whereas for a sentence, if you start ordering the words around, it doesn't make sense anymore. So that didn't really work for us either. So now what we are doing is treating our collisions as a point cloud, where you have energy deposits in some four momentum space that is basically irregular, and every single point just has a PT, eta, and a phi. And this is very similar to what's done for self-driving cars. They have LiDARs where you have these position points in Euclidean space. Then we have a set of n-dimensional vectors, like a set of particles in and their four momentum. So in all state-of-the-art algorithms that you are using for event reconstruction today, we use point clouds. The benefit of using point clouds is that we can treat them with what's called graph neural networks or transformers. So how does that work? So for instance, if we have a vector boson jet with particle constituents, we can treat them as either sets or as graphs. So for instance, here, you can treat them as a set of particles. So each particle has a 4 vector, and they have some relation to each other, some edge, some connection. Then we call it a graph. If there's no connection, we call it a set. Then what we can do, if we want to process this with a deep neural network, is that we encode all of the information of each of these particles through a neural network. So each particle becomes a neural network. Each connection becomes a neural network. We concatenate all of this together, pass it through fully connected layers that does some classification. So here we have what's called graph neural networks that act on this point cloud data, and every single state-of-the-art jet tagging algorithm we have works like this. It's a GNN on the point cloud. You can also do a graph neural network using a more clever representation like the Lund plane. And you can also add in this thing that we called attention. So attention is one of these fundamental parameters that go into what's called a transformer. And transformer in these days is what is powering AlphaFold, is what's powering GPT, it's what's powering our state-of-the-art jet tagging network PAR-T. And what's really, really cool about these networks is that they learn by themselves how particles inside a jet, how particles in an event interact with each other. The way it does that is through something called self-attention. So for instance, in the example of a sentence, if you have a sentence like the animal didn't cross the street because it was too wide, attention computes a probability of how every single word relates to the other words in a sentence. So for instance, it maps a weight of how strongly it is connected to all of the other words. So in this case, it relates very much to animal. It also looks at the whole sentence itself, which means that it can tell the difference between sentences like the animal didn't cross the street because it was too tired versus the animal didn't cross the street because it was too wide. In this case, it relates to the street. In the top case, it relates to the animal. So it's these very small subtleties it can take into account. The way it does that is very easy. It's basically just taking a dot product. So in the case of words or in the case of particle, what you do is you take a weighted sum over all of the input vectors, so a weighted sum over all of the input particles. And you take basically this weight is how related the inputs are, which can be a simple dot product between particle 1 and particle 2. In reality, particle 1 has now been encoded by a neural network, particle 2 has been encoded by a neural network, and you take this dot product between the two to see how related they are, how much they align. And then you map it to a probability between 0 and 1 using what's called the softmax function. And this very simple mechanism, basically just a dot product, is this thing called self-attention that allows the particles to interact with each other and figure out what other particles they should pay more attention to, called attention. So these weights determine the relationships between every particles of the point cloud. And if you have several attention layers, it maps onto different important features inside your event or inside your jet. So what's really cool about this is that you can take any jet or any event that you want and train this attention weight. So here you have various different particles. You have a gluon, you have a quark, you have a C boson decaying to 2 quarks, W boson decaying to 2 quarks, and a top quark decaying to 3 quarks. Without being given any information that this thing has 2 quarks inside, this thing has 3 quarks inside. Gluon is soft and blurry, light quarks are kind of narrow and hard. This algorithm, based on the weights between different particles, can give you that substructure out automatically, allowing you to basically tell the difference between gluons and quarks, essential for vector boson fusion, vector boson scattering forward jets, or a W jet and a QCD jet. So all of these developments, going from images to recurrent neural networks to point clouds, has led to a huge development. So here, if you look at how good our jet tagging algorithms are, so up Y is better versus how big the neural networks are. Down here, we are pre-deep learning in terms of sensitivity. So classical variables like N subjettiness, substructure, often used for tagging hadronic Ws or Cs. Convolutional neural networks are down here. You have message passing graphs that we talked about before, and suddenly now in 2022, transformers. These networks use physics information inside the network, so you can constrain the network to respect Lorentz symmetries, for instance. And now we are doing things called transfer learning from larger data sets, foundation models, which we will come to in the end. So going from classical machine learning like CNNs to really deep learning transformer, we have a factor of 3 gain in sensitivity, so a huge difference. Okay. Then we are also using machine learning to reconstruct very complex patterns in complex particle detectors. Now we're going to talk about detector reconstruction and how AI can help there. So in this image, what you see is the output we have from any given collision in CMS. And we need to go from billions of sensor output to reconstruct the final particles. So here you can see a slice of the CMS detector where you have the collisions happening in the center of the detector. And every single particle that's produced passes through all of these different detector material and leaves signals in the subdetectors. So for instance, a muon, which everyone connected probably knows, will basically traverse the full detector. It's a minimum ionizing particle and leaves signals in the muon chambers. And quarks basically dumps all of their energy in the hadron calorimeter. Now, when we do reconstruction, one of our main tasks is connecting information from the tracker, the ECAL, the HCAL, and the muon chambers, and we do that algorithmically. This is sequential, it's time consuming, we use Kalman filters, and it takes a lot of compute to do. So one of the things we are exploring is how you can go from doing this classically and rule-based to using graph neural networks to do the full event reconstruction. Now, these things look very, very similar. So what is the benefit of doing this classically versus using a graph neural network? Well, it's again in this parallelism you can use, the power in compute. So whereas the normal particle flow scales non-linearly with increasing input size, so the more particles you have per event, the more time you need per event to compute particle flow, a graph-based model can scale approximately linearly with the input size. So these compute benefits helps us be more efficient. Okay, then data analysis. How can machine learning help us do things completely differently? So one of the things I'm most excited about in how machine learning can help us do physics is based on the two following points. So one of the things is what I mentioned before. We need this simulation in order to compare it to data, in order to make a statement of how likely the data is. But we do already know that data and simulation differs. And if data and simulation differs, whatever you train in simulation, you will use it on data, it's suboptimal. Whatever you design in simulation and apply in data will be suboptimal. Also, we are already using the simulation to design our full analysis flow in particle physics. So we never really look at the data itself. What we always do is look at the lower part, the simulation. We always start by assuming the standard model from simulated events. Then we assume a signal hypothesis from simulated events, and we use that to tailor our search. For instance, in this case, we say this is the not interesting region, this is the interesting region. So this is very powerful, but it's obviously limited to the model of choice. So we use the simulation, which is suboptimal because it's not data. We use the simulation to tailor our search, which makes us biased to what we have a priori said we want to study. Now we're at this point where there really is no well-motivated theory. SUSY, well-motivated. Higgs, well-motivated. Now we really don't know anymore what we are looking for in terms of what's new. So for this can, for instance, be a light C prime, a graviton to 2 Ws, things like that. So how do we know we're looking for the right thing? So what I think is really powerful with machine learning is that you can do something called anomaly detection. So every time we look for something like a heavy C prime, that may be the case to 2 quark, or C prime to diboson, is that we compute these limits. And what goes in these limits, basically how good they are depends on how much we can reduce the background for a given search and how much we can enhance the signal efficiency for a given search. The problem is that every single time we do such a search for a specific signal, we need a new PhD student to tailor the search based on a given set of signal Monte Carlo to produce these limit plots, which is very inefficient. So we want to reduce the background and maximize the signal efficiency to probe hundreds of signals all at once without even giving the analysis any information about what that signal is. So instead of going from this not interesting region definition, interesting region definition based on simulated events, what machine learning lets us do is that we can learn the density of the background, we can learn the PDF of the standard model, and look for anything that doesn't look like this, doing what's called anomaly detection. There are 2 types of anomaly detection. One is called outlier detection, so really finding non-resonant out of distribution data points, and the other one is finding overdensities in distributions. And what we did in CMS to kind of use anomaly detection to see if there's anything out there that hasn't been looked for before was to say there is some heavy particles that decays into two other heavy particles that then decay hadronically. This can, for instance, be some particle A decaying to some particle B that decays to 2 quark. It looks like a boosted W, it looks like a boosted Z, it looks like a boosted top. Can we look very generically for such final states? So the way we did that is two ways. One is outlier detection. We basically learned what a typical QCD jet looks like by compressing it into a lower dimensional embedded space and decompressing it again. We trained directly on the data to learn what a typical QCD jet looks like. Now, if you pass through a jet that hasn't been seen in the usual training, a very, very rare process, this compress-decompress flow will fail, and what comes out will be very different than what comes in. And the difference between the two defines a degree of abnormality. You can call that degree of abnormality the error in your reconstruction, an anomaly score. So what we did was say we trained such an algorithm on data. If we would look for some heavy signal decaying to 2 Ws, decaying to 2 quarks, something like that, before cutting on that score, the signal would be too small. If we put a cut on this score, you can enhance the S over root B significantly and look for a new heavy particle completely model agnostically without passing in a signal hypothesis a priori. You can also use it to find over densities. So let's say you're looking for a heavy new particle that's resonant in some spectrum, and you have two different sidebands. What you can do is learn the density of the data in the sidebands and learn to interpolate that into the signal region and compare it to the data itself. Again, you're not using simulation for anything. You don't have the two biases of a signal hypothesis through Monte Carlo. You don't have any biases from training on Monte Carlo. Everything is directly on data. One of the ways you can do that is what's called koala, where you have some signal-enriched sample in data. It can be a data sideband, and a data signal region, and you have some background-enriched sample in data. Then you train a classifier to distinguish between these two regions, where this one contains both background and signal. This one contains both signal and background, but the fraction is different. And you can use that to basically train a discriminant between signal and background, completely model agnostically. So the way you can do that, if you look for a heavy new resonance, is that you say, I'm looking for a new particle here. This is my signal region data, and this is my background region data. I train a classifier to distinguish between the two regions. Then I use that classifier and apply it to data to get rid of the background events. And in that way, you can have this distribution here before a cut on the anomaly score and an enhanced signal after a cut on this score, and do a completely modeled signal agnostic search for any new heavy particle decaying to jets, 1-prong, 2-prong, N-prong. Now, the power of these methods is very cool when you don't really know what you're looking for. You can use all of these methods and search for 50, 100 new physics hypotheses in one go without having to invent 50 PhD theses, each for every specific search. Okay, then I want to talk about luminosity. So in high luminosity LHC, we have vast data amounts that we need to handle from a data point of view and from a simulation point of view. So first for simulation, generative models for simulation. If you're doing data to Monte Carlo comparisons of very rare processes, say VBS, Higgs self-coupling, you will need a lot of simulation. So here you can see as a function of the year, the total amount of CPU we will need at the LHC, where the blue line here, top line, is what we will need in the future, and the gray band is what we can afford. So in the future, we will need so much compute that it's out of our budgets. We really have to redesign all of the algorithms that are currently in use. What we also know is that 60% of that compute goes to simulation. It's this RecoSim, Sim, Gen, that amounts to 60% of the total CPU. So if we can reduce that, we are already on a very good path. So we looked at this Monte Carlo generation scheme before. Generating the hard process is very easy and fast. Doing the detector response itself, so passing those particles through the detectors using GEANT4, is extremely hard and slow. So what we hope to do is to replace this GEANT4 step completely using generative models. So the goal is to train, rather than using GEANT to generate millions of events, which is slow but accurate, we generate half of that amount with GEANT train a surrogate model, a generative machine learning model on that, and oversample from that until we have the amount of simulation we will need for high luminosity LHC. And one of the things we're using for that is what's called diffusion models. So they basically learn decay of information through noise. So you take some original input, apply Gaussian noise to that input until you have a blur left, and learns to recover the information back from that noise and get the original image. And that allows you to sample from this noise and get a real collision image out. And this is already something that's being used in Atlas. Fast Calogan is already default in the simulation scheme where you have 100 networks running and doing that simulation cheaper for you. I also want to talk about one of the biggest bottlenecks we have in the future, which is handling the data amounts inside the detector itself. So here we're talking about data acquisition and triggering. So when we are colliding at the LHC in CMS, we have roughly 1 billion collisions per second, generating a megabyte of data per collision, corresponding to a petabyte of data every single second. So for us, that's roughly the whole Netflix library of data every single second. So having to process all of this data is really, really extreme. So if we look at the time we have to process that data, here we are down here, we roughly have microseconds of time to process all of that data versus the amount of data that's going through our system. This is at this very extreme edge of what's being done, for instance, in the Google Cloud or in Netflix. So we've really been forced at the LHC to develop brand new methods for handling vast amounts of data really, really fast. Also, we roughly generate 40,000 exabytes of data every single year, which is way more than Instagram, Google Cloud, Amazon, etc. So we've had to develop our very own methods for processing this. In addition, we are located 100 meters underground, where we have roughly a petabyte of data generated every single second. Now, for us, we would prefer to keep all that data and read it out for offline data analysis. The problem is we cannot, because if we want to read out all that data, we have to put cabling inside the detector, which basically obscures the detector, and there are no silicon anymore. For instance, there are no sensor data anymore. So what we do instead is get rid of the data in real time. And this is done in the following way. We store the data temporarily inside the detector itself for a few microseconds. So no data ever leaves the detector. Then we take a subset of that data, roughly 200 kilobytes of the 1 megabyte, and we send it through high-speed optical links to a radiation-shielded cavern right next to the detector. At this point, the data itself is only stored inside the detector and has not left, and a subset is sent into this cavern. This subset is roughly 5% of the total internet traffic, so it's vast amounts of data. This is sent to what's called a level 1 trigger, where we have roughly 1,000 FPGAs that needs to decide which event to keep within 12 microseconds or so. And we need to reject roughly 99% of all of the collision events. So this whole system has microseconds to reconstruct the full event and make a single binary decision, a 1 or a 0. If it's a 0, that information from that collision is flushed and we'll never see that data again. If it's a 1, then and only then do we send a signal back to the detector that says, 1, release your data and send it to the surface. So at this point, we've rejected 99.7% of the events, and we're sending 110 kilohertz of data to the surface. That's still more data than we can afford to read out and store. So at this stage, we do another rejection on 30,000 CPUs, 400 GPUs to reject further 99% of that collision data. And only after this step do we send the data to the final storage for full reconstruction. 1,000 events per second rejected 99.9975% of all of the events. So that means this we are left with only 0.0025% of the collision events. And if you're looking for a rare process, again, like VBS, you roughly have no statistics left afterwards to do your analysis. So when we do this selection, we want to make sure we select the right data. We're fast enough to get more data through, and we're accurate in the way we select it. In the future for high luminosity LHC, we are producing way more data so that we can detect way more rare processes or new physics, which is produced basically 1 in a trillion, if at all. So the way High Luminosity LHC will address this is by producing more collision data with every single bunch crossing, so we can increase the statistics by a factor of 10. So that's great. We'll have a factor of 10 more data in the future to really probe these very, very rare processes. The problem is that with the current LHC, we have roughly 60 proton collisions happening simultaneously that we need to reconstruct within microseconds in the trigger. In the future, this will be roughly 200. So even in order to do exactly the same physics we're doing today, we need better detectors and we need better reconstruction algorithms in the trigger in order to keep the very rare events. So here we're talking about using machine learning on specialized hardware to make sure we're keeping the rarest and most precious event for data analysis. So here you can see an example of what the trigger looks like. You have calorimetry, 400 FPGAs, tracking, 200 FPGAs. Everything is merged together before you have a final yes or no decision. We have very complex charge track input, new detectors. And what we are assuming for the future is that we'll have machine learning inference in this system corresponding to 40 billion inferences during High Luminosity LHC, which is as many inferences as is done in the whole of Google, basically. So these libraries we've had to develop ourselves in order to be able to put fast machine learning algorithms into the level 1 trigger and inside the detector. These are called HL-LHC and Conifer. And what they do is basically take whatever model you have trained in your favorite language, translate it using our libraries into something you can put on an FPGA. Even if you're a physicist, you don't need to be an electrical engineer. That's led us to be able to have this benchmark of tens of machine learning algorithms in the trigger system. So what we're using it for, just 2 quick examples. One is to do machine learning inside the detector itself, where you have high radiation and the system is cooled to low temperatures. So as an example for CMS, we have a very high granularity calorimeter with depth. So you have a depth display of every single collision and with timing. So again, looking at a vector boson fusion Higgs to gamma gamma process, plus a pileup of 200. What you can basically see is that you can try to identify what is a gamma, what is a jet, simply from the depth of the detector. And you can get rid of the background by putting a timing window. So for this process, with no timing cut, you're overwhelmed by pileup. With a timing cut, you can really see the jet and the photon from this process. So very good for multi-boson searches with forward jets. The problem is that there's too many channels in the detector to read out for the level 1 to trigger. What we're doing instead is putting machine learning in the system to read out the data. So inside the detector, we have tiny chips that sends the data to the level 1 trigger, reducing the information and sending it to the trigger and to the surface. So what we're doing here is that we take all of these detector channels and we try to reduce the information. For that, we use an autoencoder. We reduce the information of the detector to a lower dimensional embedded space, and we train an algorithm to reconstruct it again. So all the essential information of the collision is in this embedded space. Then what we do is that we put this half of the algorithm inside the detector itself on the sensor. We compress the data and we send that data out to the level 1 trigger. Now you have way less data you have to get into the trigger, and you can actually read out that system. So this is something we want to do for High Luminosity LHC. And then in that system, you can reconstruct that data again. Then we also plan on using machine learning in the trigger. And we're also using that now. In CMS, we have the first machine learning-based trigger running inside CMS, doing anomaly detection. So here the idea is we're currently selecting 1% of event in the trigger, but you can imagine that new physics falls below this threshold. So how can we trigger on these events? So what we do instead is train an anomaly detection algorithm to select what is abnormal rather than the normal events. We train an algorithm to, again, as we saw before, compress the data and decompress it again. If something weird comes through, we cannot do that, and we select what is anomalous. And this is, then we select only what's above a certain threshold. And this is an algorithm we currently have running in CMS in 50 nanoseconds, recording 300 collisions per second that we can do for new physics searches. Now, in the interest of time, I think I will end with this, where I show you the two first machine learning-based triggers we have running in CMS and in Atlas for the first time taking data using machine learning. I wanted to briefly talk about what's called foundation models, but I'll leave that for the questions in the end, where we're really trying to train large models like GPT to learn the essence of physics and use that to collect better data to do better analysis. But I'll skip to the final slide. So I hope with this, I've convinced you that we're doing machine learning at a lot of different stages of the data taking, from the final data analysis to the detector reconstruction and tagging, data acquisition, triggering generative models for simulation, and it's all tools that will be needed for high luminosity LHC. And foundation models aside, we can talk about that during the question session. So thank you very much for having me, and I'm very happy to take any questions you might have.